Assalamualaikum and welcome back. Okay, today I'm going to show you how to get dv integrate over solid G using spherical coordinates. That will be equal to rho squared sine phi d rho d phi d theta. Okay, so here we have a spherical box. This is what we call a spherical box. This spherical box is obtained from having two spheres, two cones, and two vertical planes. Okay, let me show you where are the plane and the spheres and the cones. Okay, let's see here. Here we have ADBC. That would be an area on a smaller sphere, and PQRS is part of the larger sphere. Okay, so we have two spheres here. One is ABCD would be on the smaller sphere, and the surface PQRS is a part of the surface on a larger sphere. Okay, and then we also have two vertical planes. Remember, two vertical planes is really theta equals a constant. Okay, so now we have two vertical planes. Okay, let me show you where are the planes. Part of the planes would be on the ABRQ. Okay, let me change that, change the color. Let me erase the surface on the sphere first. Okay, now the part of the vertical planes would be this PDCS. Okay, so that would be a surface on part of the first vertical plane. Okay, and the second one would be ABRQ. So ABRQ would be another part of the surface which is on the other vertical plane. So we have two planes here. Okay, so the spherical box is on two spheres. One is smaller and the other is larger, and it is also on the two vertical planes. We have ABRQ, that is one on one plane. Another one is DCPS, that is on another vertical plane. Okay, and the spherical box is also on two cones. Okay, let me show you the cones. The first cone is this part here, ADPQ. That is on part of a cone. Okay, so we have one cone here. Okay, and another one is the surface BCRS. This is a surface on the other larger cone, which is like so. Okay, so this that would be another surface which is on another cone. So combination of two spheres, two cones, and two vertical planes, we have this spherical box which is on ABCD PQRS. Okay, I hope you understand this. All right. Okay, so now we want to find the volume of this spherical box. So we assume that the volume of this spherical box would be AD times AQ times AB, which is really the length times the width times the height. Okay, all right, so let's find let's get AD. So here it says AD is rho I sine phi delta theta I. Okay, so AD is this. This is really a circumference. Remember, we have the cone. Okay, we have the cone. So here AD is on the circumference of this circle. Okay, circumference of that circle. So if you remember from high school, so this bit here, this is delta. The angle there is delta theta I, because it's between two vertical planes. We have AB QR, that is on one plane, the other is on DCPS, that is another plane. So this angle here is the difference between the two planes, which is delta theta I. Okay, so we want to find AD. AD is part of the circumference for this circle here. Okay, so from high school, if you recall, if you have okay, so it's circumference, all right. So if you have a circle of radius r, the circumference would be 2 pi r. But if you only want the part of the circumference, let's say the radius is still r, but here instead of the whole circle, we have theta here, the angle. So the circumference would be equal to the theta r, okay, the angle times the radius. So here we have, if it's the whole circle, the angle is 2 pi and the circumference is 2 pi r. So if the angle is theta, we have 2 pi r over 2 pi times theta, which give you theta r. So the circumference for this part of the circle is theta r. So angle multiply with the radius. Okay, now going back to our circumference here, which is AD. So here the angle is delta theta I, and the radius would be the same length as AD. So remember from the previous video, that is really rho sine phi. Okay, rho sine phi. Remember from before? Okay, this one is rho cos phi, and this length here is rho sine phi. Okay, all right. So the angle is delta theta I. The radius is rho sine phi. So we have AD there. Okay, all right. Now let's find excuse me, let's find AQ. Okay, AQ is, okay, let me erase this. Okay, this is AQ. This is AQ, which is really the distance between the smaller sphere with the larger sphere. So the difference between the two spheres, that would be delta rho I. Okay, so the first one, the smaller sphere, the radius of the larger sphere minus the radius of the smaller sphere, then we get delta rho I. Okay, so that's AQ. Now let's find AB. AB is this. Okay, this is really part of a sphere. Okay, and then here we have a circle. Okay, again we have this radius there. Okay, and here we have the angle. So the angle is really delta phi I, because this is the angle between the two cones. Okay, because remember here we have one cone and here we have another cone. So that bit there would be the difference between the two cones, which is really equal to delta phi I, and the radius here is rho. So remember, it's the circumference of a circle. Okay, so the angle, which is delta phi I, and the radius, which is rho. Okay, now when you multiply the three, AD, AQ times AB, you get rho times rho there. So we have rho squared. We have sine phi. And then we have delta rho, delta phi, delta theta. So this is equivalent to the volume of this one spherical box. All right, so then from here we get dV is equal to rho squared sine phi d rho d phi d theta. So this is very important for you to remember, dV in spherical coordinates. All right, and then we have this theorem. So let's now your function would be in terms of rho, phi, and theta. Is not x, y, and z anymore. And then your solid G here would be all the points. Then the variable is rho, phi, and theta. So the radius, rho, phi, and theta. So the common, or the most, the easiest solid would be where rho is from a constant to a constant. So you have two spheres. One is of radius A and the other is of radius B. And we have two cones because here we have rho equals a constant and rho equals L, which is also a constant. So we have two cones. And theta is also from a constant to a constant. So again, you have a solid that is similar to this spherical box. Okay, so then here the function is still in terms of rho phi and theta, and dv here would be equal to rho squared sine phi d rho d phi d theta. And this is usually the order of integration that we use. We integrate with respect to rho first, phi first, and then theta. But if your solid is a spherical box, then the order of integration does not matter. You can do it in other 5, 6 iteration. Remember, we have the cuboid in Cartesian. Your dv can be done in 6 different ways. So same thing here. If your solid G is a spherical box, then you can do it in the other 5 order of iteration. But usually this is the order that we use: rho first, phi, and then theta. Usually that is the order that we use. Okay, for examples, I'm going to save this in the next video. Thank you.